To correctly size an equipment grounding conductor, or EGC, for a 50 horsepower three-phase motor operating at 208 volts, we need to follow the guidelines provided in the National Electrical Code, specifically Table 250.122. In this case, the motor is protected by three 400 amps non-time delay fuses. Let's walk through the steps to verify that a number 3 AWG EGC is the correct size. Firstly, we'll determine the ampacity of the branch circuit conductors. The formula to calculate the full load amps, or floor, is as follows: FLA equals 125% times rated horsepower times kVA per horsepower divided by voltage. Given a 50 horsepower motor with a typical kVA per horsepower ratio of 1/1.15 and a voltage of 208 volts, the calculation is FLA equals 125% times 50 horsepower times 1/1.15 divided by 208 volts. This results in an FLA of approximately 32.4 amps. Secondly, we need to determine the maximum overcurrent protection device rating. The overcurrent rating is calculated as 125% of the FLA. Using the previously calculated FLA of 32.4 amps, the overcurrent rating equals 125% times 32.4 amps, which equals 40.5 amps. Thirdly, we select an overcurrent device rating that is not less than the calculated value. In this scenario, the overcurrent device rating is 40 amps. Fourthly, and this is where Table 250.122 comes into play, we determine the size of the EGC based on the highest fuse rating among the three phases. According to Table 250.122, for an overcurrent protected device rated at 400 amps, the corresponding EGC size is number 3 AWG. Therefore, based on this step-by-step verification process, a number 3 AWG EGC is indeed the correct size for a 50 horsepower three-phase motor operating at 208 volts and protected by 400 amps non-time delay fuses. Table 250.122 of the National Electrical Code provides the minimum size requirements for equipment grounding conductors based on the rating or setting of the overcurrent protective device in the circuit ahead of the equipment. This table is essential for ensuring electrical safety and proper grounding in various electrical systems. The table lists the size of the equipment grounding conductor in AWG or circular mills for both copper and aluminum conductors, corresponding to different overcurrent device ratings in amps. For example, for overcurrent devices rated from 15 amps to 20 amps, the minimum size of the copper equipment grounding conductor is number 14 AWG. As the overcurrent device rating increases, the size of the equipment grounding conductor must also increase to provide a low impedance path for fault currents. It is very important to always consult the latest edition of the National Electrical Code in Table 250.122 to ensure compliance with the most up-to-date requirements and to select the appropriate size of equipment grounding conductor for a given application. In addition to Table 250.122, it's essential to consider other factors that can affect the size and selection of equipment grounding conductors. One such factor is the length of the circuit. Longer circuits may require larger equipment grounding conductors to compensate for voltage drop and impedance, ensuring effective fault current carrying capability. Furthermore, the type of raceway or cable used to enclose the circuit conductors can also influence the selection of the equipment grounding conductor. Some raceway systems, such as metallic conduits, can serve as equipment grounding conductors themselves, while others may require a separate equipment grounding conductor to be installed. The material of the equipment grounding conductor, whether copper or aluminum, should also be considered based on the specific application and environmental conditions. Copper is generally preferred for its higher conductivity and corrosion resistance, but aluminum may be used in certain situations provided it is properly sized and installed. Understanding these additional factors is crucial for ensuring the safety and reliability of electrical systems. Improperly sized or installed equipment grounding conductors can lead to hazardous conditions such as electrical shock, fire, and equipment damage. Therefore, it is essential to consult with a qualified electrical professional and adhere to all applicable codes and standards when designing and installing electrical systems. Remember to always prioritize safety and follow best practices to ensure the proper functioning of electrical systems and the protection of people and property. When dealing with electrical installations, always consider the potential for harmonics in the system. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz in the United States. Nonlinear loads such as variable frequency drives, electronic ballasts, and some types of power supplies can generate significant harmonic currents that can flow through the electrical system and affect the sizing of equipment grounding conductors. In systems with significant harmonic content, the equipment grounding conductor may need to be oversized to accommodate the increased current flow. The NEC provides guidance on sizing equipment grounding conductors in systems with harmonics, typically requiring the equipment grounding conductor to be sized at least equal to the phase conductors. It is very important to conduct a harmonic analysis of the electrical system to determine the level of harmonic distortion and to select the appropriate size of equipment grounding conductor accordingly. Ignoring harmonics can lead to overheating of the equipment grounding conductor, nuisance tripping of circuit breakers, and other electrical problems. Another important consideration when sizing equipment grounding conductors is the presence of sensitive electronic equipment in the system. Sensitive electronic equipment, such as computers, data processing equipment, and medical devices, are susceptible to damage from voltage transients and electrical noise. A properly sized equipment grounding conductor can help to mitigate these problems by providing a low impedance path for fault currents and by reducing the level of electrical noise in the system. In some cases, it may be necessary to install a dedicated equipment grounding conductor specifically for sensitive electronic equipment. This dedicated equipment grounding conductor should be isolated from the regular equipment grounding system to prevent noise and transients from propagating to the sensitive equipment. Additionally, the equipment grounding conductor should be bonded to the building's grounding electrode system at multiple points to ensure a low impedance ground path. It is recommended to consult with an electrical engineer or a qualified electrical contractor to determine the appropriate grounding strategy for systems with sensitive electronic equipment. The proper installation and maintenance of equipment grounding conductors are essential for ensuring their effectiveness and longevity. Equipment grounding conductors should be installed in accordance with all applicable codes and standards, and they should be protected from physical damage and corrosion. Connections to equipment grounding conductors should be made using approved methods such as compression connectors or exothermic welding. It is very important to periodically inspect equipment grounding conductors for signs of damage or corrosion and to repair or replace them as needed. Loose or corroded connections can increase the impedance of the equipment grounding system, reducing its effectiveness and increasing the risk of electrical shock. Additionally, equipment grounding conductors should be tested periodically to verify their continuity and impedance. This testing can be performed using a ground resistance tester or a low resistance ohmmeter. Any problems identified during testing should be addressed immediately to ensure the safety and reliability of the electrical system. When working with electrical systems, it is essential to understand the difference between equipment grounding conductors and grounding electrode conductors. Equipment grounding conductors provide a low impedance path for fault currents to return to the source, tripping the overcurrent protective device and energizing the circuit. Grounding electrode conductors, on the other hand, connect the electrical system to the earth, providing a reference point for voltage and helping to dissipate static electricity. Equipment grounding conductors are sized based on the rating of the overcurrent protective device, as specified in Table 250.122 of the NEC. Grounding electrode conductors are sized based on the size of the service entrance conductors, as specified in Table 250.66 of the NEC. It is very important to install both equipment grounding conductors and grounding electrode conductors correctly to ensure the safety and proper functioning of the electrical system. Improperly installed or sized grounding conductors can create hazardous conditions and increase the risk of electrical shock. In addition to the requirements outlined in the EGC, there may be local codes or regulations that govern the installation of equipment grounding conductors. It is very important to check with the local electrical inspector or building department to determine if there are any additional requirements that must be met. Local codes may specify different sizes or types of equipment grounding conductors, or they may require additional grounding measures to be taken. Failing to comply with local codes can result in fines, delays, or even rejection of the electrical installation. Therefore, it is essential to be familiar with all applicable codes and regulations before beginning any electrical work. When designing and installing electrical systems, it is also essential to consider the impact of electromagnetic interference, or EMI, on the performance of sensitive electronic equipment. EMI is electrical noise that can disrupt the operation of electronic devices, causing them to malfunction or produce inaccurate results. Equipment grounding conductors can play a role in reducing EMI by providing a low impedance path for noise currents to return to the source. However, to be effective, equipment grounding conductors must be properly installed and bonded to the equipment enclosure and the building's grounding system. In some cases, it may be necessary to use shielded cables or other EMI mitigation techniques to further reduce the level of electrical noise. It is recommended to consult with an EMI specialist to determine the best approach for minimizing EMI in sensitive electrical systems. The size of the equipment grounding conductor plays a crucial role in electrical safety and system performance. An undersized equipment grounding conductor may not be able to effectively carry fault currents, increasing the risk of electrical shock and equipment damage. An oversized equipment grounding conductor, on the other hand, may provide better protection against EMI and voltage transients, but it can also be more expensive and difficult to install. The correct size of equipment grounding conductor should be determined based on a thorough analysis of the electrical system, taking into account factors such as the rating of the overcurrent protective device, the length of the circuit, the presence of harmonics, and the sensitivity of electronic equipment. It is very important to consult with a qualified electrical professional to ensure that the equipment grounding conductor is properly sized and installed. Remember, electrical safety is everyone's responsibility. Always follow safe work practices when working with electrical systems, and never take shortcuts or compromise on safety. If you are not qualified to perform electrical work, it is recommended to hire a licensed electrical contractor to do the job. Electricity is a powerful force that can be dangerous if not handled properly. By following the guidelines and recommendations outlined in this discussion, you can help to ensure the safety and reliability of your electrical systems.